Your output is not dependent. Hello. So I think please just send the message now. Okay, well, the problem is please ask us. You can like this. I will be. You can say that I mean welcome. All the others to ask him to basically note it only I know that. So I mean somebody will be a hearing voice coming. Voice is getting there. No panic. Already has to connect it and so, good afternoon, everyone. I am Saravana, scientist from CSI of CSMCRI. On behalf of the organizing committee, I warmly welcome you all to this 61st Iconic event entitled Industry Method Desiccant Products in 2022. On behalf of the organizing committee, I warmly welcome you all to this 61st Iconic event entitled Industry Method Desiccant Products in 2022. Disconnect करके डिस्कनेक्ट करके कर लेना. close this page. This is a quick thing.
But the morning was perfect. Morning was perfect. Now you can see. Just ask me where you can hear us. Now it's not coming.
Comparing calcium.
Just ask him whether you can.
Hello, am I audible? Ritvik,
Yes, sir.
so shall I go on?
Please continue.
Sorry for the technical problem. Good afternoon, everyone. I am Saravanan, scientist from CSIR CSMCRI. On behalf of the organizing committee, I warmly welcome you all to this 61st iConnect event entitled Industry Meet on Silicon Products 2022. I would like to express my sincere gratitude to our eminent speakers for accepting our invitation and join with us today to share their rich experience on silicon products. Before we go ahead with scientific presentations and very insightful discussions, let me quickly brief out what is iConnect event series. As many of you are aware, these events are the part of celebrating the 75th year of India independence. In this context, the Science and Technology Ministry hosted this iConnect event series with an attention to draw upon the rich expertise, competence of leaders from both government and industry to sit together and discuss the potentials towards the collective collaborations and contributions for the economic growth of the nation. In this context, again, the particular event may likely resound the possible interplay between CSIR and industry to strengthen the research activities on silicon products. The organizing committee has built up this event with stimulating talks from versatile technological leaders to give you an overview of what one can expect from the second most abundant element, silicon and derived compounds. With this brief introduction, now I humbly request Dr. Kannan Srinivasan, our beloved director of CSIR CSMCRI, to deliver the welcome and inaugural address. Sir, please.
Thank you, Dr. Saravanan. You can load my presentation. At the outset, I sincerely welcome all the colleagues, the invited speakers, Dr. Swapan, Dr. Bijan, Dr. Dhananjay Sabde, for this iconic event, Industry Meet on Silicon Products. As Dr. Saravanan mentioned about the iconic, the purpose of the iconic event is largely to create a kind of an interface between the industry and the research institution to have a kind of a better collaboration and forged partnership for solving the problems of the industry and solving and in turn solving the problems of the society and creating a kind of a wealth for the nation. That's the fundamental objective of this iconic event. And this whole idea of iconic started. I mean, you've been hearing about it, that many of us, what do you call, are aware during the pandemic. We have been put into kind of a different kind of hardships, and the major thing that basically helped us was the science and technology tools, and where I mean there's a kind of a fantastic partnership of industry and research institution and academic institution have been demonstrated for quicker and faster translation. And this particular what do you call the event was also urged to create a kind of an augmented effort as we are celebrating the 75 years of Indian independence in the form of Azadi Ka Amrit Mahotsav, where I mean we wanted to reinvigorate and strengthen the industry research academic interactions, and the idea was born, the iconic idea was born, where 75 such industry meets are going to be held with the different ministries, not only with CSIR, with all the Ministry of Science and Technologies and Earth Sciences and Space and Atomic Energy. Every ministry has been associated with this iconic event, which largely, as I said, about the forging the partnership. So with this backdrop, I once again, welcome all the participants, all the industry stakeholders, the entire CSIR family who are basically attending this function, and my own CSIR family, and all the invitees who are attending this event through virtual mode across the country. A warm welcome to you all on this great occasion. And this particular event also provides an opportunity to briefly introduce about the organization which we belong also, because I mean many a times many of the industry participants, many of the the other academic organization have also been invited for this particular these kind of an events, and to give a kind of a brief idea about CSIR, especially in the context of chemical sciences, I will just briefly run through a short presentation which will give you a kind of a flair what CSIR is and what chemical sciences laboratories of CSIR are doing in the service of nation. If I were to CSIR as an organization is a kind of a pre-independent organization. This was actually, I mean, it's a registered society in the year of 1942. As we are celebrating 75 years of Indian independence, we are celebrating 80 years of presence of CSIR. And in fact, I mean, there is a program called as 80 Success Stories of CSIR, which you can, see it in the YouTube, where different success stories of CSIR are portrayed through different kind of programs. And this is one of the beautiful things one can always watching. So what is the purpose of an organization when it was basically instituted? The purpose was to have a kind of a greater connect between the industry and the research institution. And this was a kind of a focus which is strongly backed by the kind of a, which is strongly backed by the kind of a science. Give me my computer. Okay, which is strongly backed by the kind of science, and at the same time, it should have a kind of a relevance for the industry. And with this kind of a backdrop, the CSIR organization was born. And for the ease of what do you call clustering, we have roughly around 57 laboratories and are clustered into 5 different domains in chemical sciences, engineering sciences, information sciences, physical sciences, and biological sciences. The number which is given in the brackets or the number of labs associated with this particular kind of domains. And if you were to see, these are the different kinds of the labs which are in each of the sector. And it is very important. Today's topic being relevant to that of chemical sciences, we have around 9 chemical sciences laboratories spread across India, working on different kind of topics, ranging from agrochemicals to pharmaceuticals to specialty materials to inorganic chemicals to polymeric chemicals to leather chemicals to bio-based chemicals to natural products to any kind of what do you call chemicals that one is basically associated with. We have been the CSIR has been associated on different domains of the chemical sciences across the spectrum of chemical industry. And to have a kind of a further ease, CSIR is what do you call catering to since many of the labs have a kind of a interdisciplinary concepts and the better connect with the kind of a ministries and with the society. So we have made the programs of the CSIR not in terms of the laboratories, but in terms of themes, where these themes makes a kind of a better connect with the stakeholders. Like CSIR, all the 37 laboratories or somewhere or other are working on one of these 8 themes, and these 8 themes are aerospace, electronics, instrumentation, and strategic sector, agriculture, nutrition, and biotechnology, chemicals, including leather and petrochemicals, civil infrastructure and engineering, ecology, environment, earth and ocean sciences and water, energy and energy devices, healthcare, mining, minerals, metals, and materials. If you really see these domains, this would encompass almost all the what do you call topics which are relevant for a technology-centric process or a product development to be what do you call catering to the industry and society. So with this, I'm going to talk about that since this particular event is largely to do with the chemical sector, and I'll be talking about what CSIR has been doing in the domain of chemical sector and what its vision and goals are. If I were to basically talk about the vision of the chemical sectors of CSIR laboratory, it wants to lead Indian R&D in the sector of chemicals with a focus on globally benchmarked technologies that are economically, environmentally, and socially acceptable with lesser carbon, energy, and water footprint, leading to a sustainable chemical industry. What does it mean? Okay, I think the chemical industry is one of the largest what do you call economy contributing industry of any nation, and India is no exception. And if you were to basically look at it, the industry and the 21st century will have the chemical industry in a kind of a different expectations. Rest alone for many of the industries, chemical industry has a unique challenges where the processes needs to be a bit more environmentally friendly, and it has to be sustainable without what do you call compromising the footprint, which are extremely essential for the planet to survive, whether it is on the climate change or whether it is on the energy resilience, or whether it is on the what do you call survival through different kind of what do you call sectors. And this chemical industry plays a very, very critical role. And sustainable way of making chemicals is going to make a kind of a different paradigm in the next few decades to come, and 21st century will be witnessing chemical industry in this particular manner. And in this, along this kind of a vision, the chemical sector, chemical sciences laboratories of the CSIR are largely concentrated on 6 subverticals, namely agrochemicals and pharmaceuticals, performance chemicals and smart materials, petrochemicals, coal, waste, biomass to chemicals, which means any kind of carbon which is available is put into a kind of what we call useful chemicals, and marine chemicals and specialty inorganics, which is basically the today's topic. And for those of you who have attended in the morning session, marine chemical sector was discussed in the morning, and now we are talking about in the context of silicon. We are going to discuss about on the specialty in the context of specialty inorganics. We'll be discussing about the silicon-based compounds and polymers and sustainable bulk chemicals, specialty and leather chemicals. These are the different subverticals where different kinds of the chemicals are going to be what you call tried out, and the processes, the products are going to be made under these 6 verticals. And chemical sciences laboratories have been contributing in the last 7 to 8 decades very significantly in the growth of the nation. And the entire chemical industry, which is what you call sprung out of post-Indian independence, some way or other, CSIR has been associated in the development, along with many other research institutions of this country. With this, backdrop, I just wanted to give a kind of a flag about a few of the recent achievements, and these are very, very new achievements in the chemical industry sector. These are only select examples. I mean, the achievements of the chemical sciences laboratories would itself be a kind of a separate topic, and in view of the time, which is already, I mean, I'm exceeding it. So I just wanted to give a kind of a brief 3 examples. One on the isobutylene derivatives done by one of the CSIR labs for making a different organic compounds like para-tetrabutyltoluene or para-tetrabutylbenzoic acid for a company in Mumbai. And likewise, I mean, there's a pilot facility for making of azelaic acid from oleic acid, where I mean a kind of a new way of doing chemistry. As I said, sustainable way of doing chemistry is very critical, and here I mean a continuous processing is demonstrated, where a commercial plant is likely to what do you call come up with this kind of a technology in the year to come. And the last one being a kind of a potash from the distillery spent wash, which is again a kind of a distillery spent wash, being a kind of an environmentally a difficult problem to solve in, which is also having a kind of a rich source of organics and potash. And the CSIR has intervened in the recovery of potash, and then what do you call, making it a kind of a with an endeavor of making a kind of a what do you call potash, reducing the kind of an import of potash in the nation. And this is basically the commercial plant in Maharashtra, which is a 60 KLPD distillery producing few hundred tons of potash. And these are only a kind of a select stories, and these are some of the prioritized areas that chemical sciences sector teams are going to work on, which I have broadly covered in the in my earlier discussions also. And this the specifics of these chemical verticals, especially in the field of all these domains, are demonstrated in this slide, given in this slide rather. And if you were to look at it, today's topic would be on the marine chemicals and specialty inorganics. And as Dr. Saravanan has talked about the importance of silicon, I'm sure that those who are most of the people who are attending this event are in one way or other related to this element silicon, which is, as Dr. Saravanan said, a second most abundant element on the earth crust. It's one of the greatest advantage of silicon is it is omnipresent across. It doesn't have any discrimination across the geopolitical, geoclimatic regions. Everywhere is resources available. So but at the same time, making a kind of a compounds out of this is going to be a kind of a very, very challenging task. In fact, I mean, in many of the silicon compounds, even today, we are importing to an extent, and there is a huge opportunity for us to what do you call chip in and create a kind of a niche competence on silicon-based chemistry by developing some sort of a silicon-based products and make India to be a kind of a great nation in terms of silicon-based compounds. In fact, I mean, the speaker who is next to me is from a company which is one of the world leaders on silicon-based compounds. So this is strongly gives a kind of a flavor that, I mean, the CSIR has the competency for contributing through their chemistries and chemical engineering skills for developing these kind of a silicon-based compounds. So with this, I mean, I conclude here. For any of the what do you call suggestions or wanted to have any kind of a clarifications, you can be in touch with any labs, or as a kind of a coordinating institute, you can be in touch with this our lab, so that we can connect you with the different kinds of institutes which are having their unique competences. With this backdrop, I once again welcome you all for this what we call iConnect event on
CSIR and chemical. With this, now we are moving to the technical session. In the technical session, we have our first invited speaker as Dr. Ankush Biradar. I would like to highlight one thing here. CSIR, CSMCR, right, has worked in silicon chemistry since the 70s, particularly in the area of precipitated silica like rubber grade and aluminosilicates like detergent grade zeolites. So several CSIR, CSMCRIs IPR protected processes have been deployed commercially across the country. With this brief highlight about CSMCRI, I invite our speaker from our own department, Dr. Ankush Biradar, who received his PhD from the University of Pune in association with the CSIR National Chemical Laboratory, NCL. Then he moved to Professor Asifa's laboratory at the State University of New Jersey, USA, for his postdoctoral research. Presently, he is a principal scientist in Inorganic Materials and Catalysis Division. With this, I invite again Dr. Ankush to deliver his talk on the glimpses of silicon proposals what we received in the past 2 years. Dr. Ankush, please.
Thank you, Dr. Sir.
just asking whether, I mean, you can.
Now,
Just ask.
hello, Prithvi.
Yes, sir. So please continue.
silicon and what are their importance. But as such, as a country, we are going. So and being a silicon, because it is one of the highly bipolar molecule, has a high ionic potential, as well as we can divalent, so ionic potential is high. So that's what these silicons can be modified in a different chemicals, but doing different chemistries, engineering, as well as processes. So by this, as this silicon chemistry is very old, and there are numerous applications have been used. For example, like electronics, we are whatever the mobiles we are using because of the silicon we are using. But as a country, we are we are just produce 60 thousands of silicon wafers, and that of our neighboring countries, they are producing about 7 million tons of this silicon wafers. And the other things like you can have the silica materials like we can use it in the healthcare, we can use it in oil and gas, we can use it in maybe in automobiles like a tire and making the enforcing material, maybe in defense application, constructions like making cements and all. And this particularly the silicon chemistry is very beautiful, where we can play around and we can make different compounds. But what happened very recently, as we revisit some of the forgotten technologies, so country is growing. At the same time, we are not working on this country, though we have earlier we have made it. But for example, what we have forgotten, so we want to relaunch this process. For example, zeolite, which is a detergent grade and plastic grade. We in the year of 2019 and 20, we purchased from, we imported from 70 crores of this one. So that means though the technologies are available around this, but those are not enough to make it. With this backdrop, we thought of can we make this process reinvent and we can make country our own sustainable with focus goal. With this goal, what we thought of, as we can do a different chemistries like silicon, silicate, silate. This silicon chemistry basically based on their particularly applications. Can we make a focus on it? So that's what we have invited a proposal. On that proposal, we can divide basically based on is the research focus is very mellow down. So we want to make it more again and make this compound this industry more wider with the local industry as well as the international industry. Make it really a good proposal. So accordingly, we have invited across the proposal in this silicon mission, and there are numerous laboratories, around 11 laboratories to part, and they have submitted a proposal. And most of the proposals we have divided into basic research as well as the translatable research, and where which are directly a compound can be delivered or new research can be delivered in a particular time. Particularly one, so I'll be going now in the detail of the proposal we received. Those have already some proven TRL levels. One is to make this precipitated silica from abundantly available rice husk. As India is one of the farmer country, so we majorly grow the rice husk, and which is yearly it is produced about 4 million tons per year. But the problem is rice husk is generally we have to disposal problems, we have to burn, and that during this burn we generate lot of carbon dioxide and environmental problem concern. And that ash, whatever the burn ash is consist of, about 75 to 90% of silica. And from that silica, we have to make a unit operation to make a particular grade of silica. But all this process is one of the energy extensive process, as well as generate lot of waste, as well as so we need to reinvent these processes to make direct utilize it. As I said, the silica is one of the base compound, is one of the highest cumulative color is more than 6.8% growth is recorded, and these all silica is used in different grades like rubber, tire grade, food grade, paint, coating, and industry. So having this enormous opportunity in making the silica, one of the proposals we received to make this silica from the rice husk, which is not, we are not burning now. So what we have, the proposal is proposed is to make that use the direct biomass and make the digestion and process and develop the beautiful silica with the different grades of silica. They propose that to make a 3D silica which has the particular properties, and due to that property they can be used for the different application. One application is proposed as aerospace and defense application because of having their particularly bulk density, thermal conductivity, so the soldiers can be used and it can be protect them at the same time. The another proposal we received it to make a silica from direct again silica rice husk. In this case now the proposal is proposed, basically they are actually working on to make basically this rice husk to a silica using cavitation process, that is mechanochemical thermodynamic cavitation by mechanical process. The beauty of this proposal is we can generate a silica with particular shapes and size, and the silica can be continuously, we can generate, can be pilot up to 1 kg level, and this silica, proposed silica can be used directly without any doing all this energy intensive process. The another, so we propose that we can use in different applications. The another way of, as I said in my first application, the rice husk is directly burned. It is made the ash, and from that ash we can make some chemicals, and that like sodium silicate. That sodium silicate we can use for precipitated silica. CSMC particularly, as CSMC we have developed this process, and this precipitated silica has different grades of silica having the different properties. Particularly those can be used in rubber, making the tires particularly, as well as toothpaste grade silica we have prepared. And this technology we have already we have developed at 1 kg level, which can be a ready to transfer technology. So another way of one proposal came in this mission is not only the silica rice husk, but we can use other biomass, like another most produced in India is sugarcane. So after extracting of sugarcane, the bagasse is remained. This bagasse is about 70 million tons of bagasse produced in India particularly, and we are the second largest producer as this one. But generally, this bagasse is burned off to produce the steam, and that is for generation of electricity. But after that, producing the lot of ash is generated, and that ash consists of silica, and that silica we need to harness, and that we can use for different applications. So one proposal is mentioned is here. So they have proposed that basically they can make this from the ash to a silica, and that silica can be utilized for different applications. For example, separation of capturing of CO2, or conversion of control of VOC and all. So this is the proposal, basically two different grade, starting material of silica, starting material of precursor of bagasse vanilla husk to make the different grades of silica. Another proposal is to make basically a material which has a different color, because we as an Indian we love to make different colors. We have the different applications in different way. But the problem is how to make this color grade. So one proposal is we actually received, and they are already shown at TRL level more than 3, where the proposal is to make this functional silica using the silica sand. As silica sand, we know, as we discussed earlier, silica consists of quartz, different variety of things. One is they want to use quartz, and from that quartz they can make a different silica grade, which has the property of IR reflective, as well as they can make a formulation basically, or they can coat basically, and making out they can grow also different metals to make metals to make the different colors. And these colors have definitely a different types of applications, and which can be used enormously in different products. So this is one of the excellent proposals we received. They have already demonstrated in this mission. The other thing is the silica is not only to use for a cement or making the any tires or thing. The one proposal we received, they proposed that can the silica be used for the leather applications, where they propose to make the different functional silicas, and that made functional silica they can basically tan with the leather, and that leather application which can be used for the making the different grades of leathering. The proposal mentioned that they propose that again use one of the biomass to make this silica, and this silica they can use for again very clean as well as for different applications. Not only a silica, they want to use the silanes kind of compound, where the silanes they can functionalize the leather, and by functionalized leather they can be used for the hydrophobic nature they want to create, and that hydrophobic nature of the that leather have the different properties than the original, and it will be the more durable, more valuable, and at the same time we have this our own indigenous technology. The another technology is to make basically again silica function silica, but in this time now they want to take the silica, and that silica they want to coat with the polymer, and that polymeric membrane they want to show different properties. By these properties basically based on their fine tuning of the different parameters to take the flexible materials. The another, as I said, quartz, because we as a Indian, as I said, India is looking for the alternate of energy, and solar and the photovoltaic cells are the one which can see some light that we have a promising this one. But at the same time, the photovoltaic cells needs the silicon, and India is not producing that much. We are mostly depending upon the other countries who are producing. So one technology we can develop basically in this one, and from our own as indigenous raw material, that is quartz and silica resources, to make this basically silicon vapor, pure more than 99% of the silicon. So to make this proposal, the objective of this proposal is basically to low grade quartz to make the silicon vapor using engineering parameters. The another proposal we received basically, these are now the futuristic project which have maybe some basic knowledge or some papers have published, not patented, but the technology can be developed. One is such technologies can be used this silica for chemical separation. As we know that chemical separation is one of the major challenge, particularly when it comes to the chiral chemistry. So we received a proposal. We are basically with the CSR or working on it to make the silica modified silica, or make the chiral zeolite silica, or make the polysaccharide based silica gels which can use as a separating agent, or make a column, or make the easily separable chiral molecules. Another proposal is again this silica can be used for the biomedical applications, because one of the issues we are facing is how to make the biocompatible silica. As I said that in my first slide, that the silica is not only is available but is non-hazardous to nature. So and it is biocompatible. So the one proposal we received to make the engineering tissue, basically engineer the bone tissue engineering or oral care to by modifying the different like metals like sodium, potassium, calcium, magnesium to make it work, or either bone filler or antibacterial properties of this one. The another proposal we received is to make this silica to make as a wound healing properties. So they propose to modify the silica in such a way that the toxicity should be low. The another also we received a proposal to develop a microorganism from the deep sea to make the silica. From that microorganism, the silica can be made. So that has a particularly different property, which can be definitely from the chemical process. The another very important property I said in this silicon carbide, because as we know the silicon carbides are very useful in all the industries, because steel, automobile, and all these industries are growing up. So these carbides are required. And most of the carbides we are importing again from the neighboring countries, which has very high stability, which can be used and without any property. So one should look on this carbide, and we thankful to the other CSL or CSL laboratories. They have proposed this one, and they wanted to develop a silicon carbide at even at 1 kg batch scale. Also, the other proposal is to make basically zeolite coated silicon carbide to remove the NOx, SOx from the removing gas, the industry effluent gases. The another important one more proposal is we received very important, because now we know that carbon is one of the best compatible to all the living lives. So one is neighboring metal is silicon, and it is not that much used in the basically in this one application. So the what I can put that. So that we want to make replacing that one of the metal with the silicon, which can increase the lipophility. That means which will be very analogous. We can whatever the drugs already in the market, for example, Tracine, Lacocine, we can make the analogs of the silicon, and that silicon, if you make the similar silicon, and that will be the value addition. And those kind of drugs, basically, not only drugs, even we can synthesize the peptide and based on the silicon amino acid, and those amino acids can be used as a drug. So this is one of the another important proposal we received, and which can be helpful not only for the other industry, but in the medical industry also it will be adopt. So in this contest, so we have received very excellent proposals. Those are more than TRL levels. Those can be directly a focused application, and the already IP is secured. So if you take a little bit up, one more step up, so we can be focused product can be developed. At the same time, we have received enormous proposals, and those enormous proposals can basically grassroots the research of next generation, next to 5 to 10 years, to make our India as a silicon hub again. And this proposal will basically not only benefit the CSR, but overall it will benefit all the country. And so this will be basically when we are celebrating the 75th year of Azadi Ka Mahotsav. So this is one of the I feel that this is one of the best proposal we have received, and we are working on it. Thank you very much for this.
Thank you, Dr. Ankush, for showing us the overview of CSR approaches towards the silicon-derived compounds. Considering the time limitations, we are skipping the question session and now moving to our next invited speaker, Dr. Sopan Ghosh. I welcome Dr. Sopan Ghosh and would like to introduce him to the audience. Dr. Sopan Ghosh received his PhD from Indian Institute of Technology, Kharagpur in the year of 2000. Then he moved for his postdoctoral research at the Technical University, Netherlands. The very initial, he started his industrial career as a research engineer at ArcelorMittal R&D industry at Belgium. He also served as a director of Green Coat Chemicals Private Limited in the period of 2010 to 2013. Later, he moved to Asian Paints as a chief manager technology, and has delivered several pioneering products. Dr. Sopan Ghosh is presently working as a technology leader, R&D innovation at Pidilite Industries Limited, Mumbai. Dr. Sopan managed and coordinated both industrial and government-funded projects in the field of coatings as well as knowledge development on new coatings related ideas for metallic substrates, especially for steel. In addition, he has published books such as Functional Coatings by Polymer Microencapsulation and Self-Healing Materials, Fundamentals Design, Strategies and Applications. He also published several research papers in international peer-reviewed journals and also the co-inventor of several patents in the field of emulsion polymers, anti-corrosive thin organic films, and functional coatings. With this brief introduction, let me invite Dr. Swapan Ghosh to share his understandings of how silica particles can be incorporated into polymeric systems for some of the exemplary applications. Dr. Swapan, please.
Thank you so much for the warm welcome and the introduction that the few words you talked about. Concerning today's presentation, the topic that I'll be covering is silica incorporated polymeric materials. Now here, basically the different so the control is with you or yes. So the different topics or different parts that I'll actually talk about, which will begin with an introduction to composite particles, then different type of synthesis strategies, so which will include techniques, how can you incorporate inorganic materials to organic polymer matrix. Finally, I'll talk a little bit more in detail about the technique of emulsion polymerization. How can we exploit this technique to incorporate, for example, silicon oxide to polymer, and then some sort of challenges when you talk about these composite or hybrid materials. And finally, I'll conclude with some concluding remarks. Coming back to the composite particles, so you can see that the composite particles are nothing but marriage between organic and inorganic materials. From organic side, we can think about the properties like, for example, organic materials are very soft, polymeric materials are very soft. So you can think about the flexibility and elasticity, which are the critical properties which can come from organic materials. Then others, they are of low density, porosity index, conductivity is low, usually they are of poor thermal stability. Then from inorganic material side, the hardness, which is the most critical one, which we can bring, hardness in the sense that it is strength and brittleness of the material. Then they are of higher density, higher refractive index, higher conductivity, and higher thermal stability. The meaning is that we wanted to combine this organic and inorganic. We can actually combine a set of properties. So we can have a composite type of properties which can develop out of these materials, the hybrid materials. Now coming back to these composite particles, what you can say that there are several routes which have been established to design composite particles. And broadly, if you can look them, they can be classified into two based on the nature of the precursor that is used to formulate this type of composite particles. For example, in one case, in the left side picture, if you see the first picture, you can see that, for example, this is the inorganic particle, that is silicon oxide here, and that is a preformed particle. So there are two ways. One is that we can use a preformed particle, or we can also synthesize using the salt gel process. In a reactor, you can synthesize the silicon oxide particles, and in the same reactor, you continue the further polymerization reaction. So when it is a preformed polymer particle, then monomer, initiator, surfactant, all are added, and then polymerization is conducted, and we can have a composite particle where silicon oxide will be coated by a polymeric material. The option B is we can do the opposite one. We can take a polymer particle, and then there in the presence of the polymer particle or polymer latex, we can add inorganic precursor, metal oxide, metal salts. The way we like to have those inorganic matrix that we want to build. For example, you can use, in case of silicon oxide, we can use different type of silicon precursor, and we can build those silicon particles on top of the latex. But usually in most cases, what it is observed, that silicon particles actually goes inside the polymer materials. The other part is that these silicon particles, they're of very important in terms that they will provide very good strength, hardness, flexible modulus, creep resistance, and they are very much important when you think about an adhesion. To improve adhesion of a system, they are of very much importance. And the good thing here is that silica is biocompatible and it is resistant to a wide variety of pH changes, and it is multifunctional. You can actually modify the silica particle and create different type of functionality. Based on that, a different set of composite particles can be made. Now coming back to synthesis strategies. So basically there are three major techniques where we can think that silica can be incorporated in polymers. The first one is blending. So blending is nothing but just mixed a preformed silica particle with the polymer matrix, blend it together either by solution blending or by a simple hot blending process. Then the second one is salt gel process, which all we are familiar with. But in this case, if you have to have silica inside polymer matrix, then in that case you have to use polymer latex, and in presence of that, we have to conduct the salt gel process. Third one is in situ polymerization. In situ polymerization, this process involves that nanosilica will be dispersed in a monomer solution, and then further a polymerization can be carried out. Now, in general, when you would like to take, let's say, inorganic material, in this case silicon oxide, to a polymeric matrix, the first stage is very often we need the surface of this silicon oxide particle must be modified with certain functional groups. And then these functional groups actually have the anchor point for the polymerization, the polymer chains to anchor with this group. When this polymerization takes place, then we can have different type of morphology based on the reaction condition, based on the monomer silicon oxide ratio, based on the modification that we are doing on silicon oxide particle, and we may have different type of morphology. For example, there is a core cell morphology, we can have star cell morphology, we can have matrix morphology, we can also have even, for example, a raspberry type of morphology. Now blending, the first one is blending solution and wet blending. There are millions of examples available here, but just to say here that a thermoplastic polymer is usually softened, it is mixed with silica to form polymer silica type of composite, and then that can be extruded through an extruder, or even it can be used, an injection molding machine can be used to mix those two, and then finally extrude it to give some shape of some articles and so on. So this mixing, typical example, for example, polypropylene with nanosilica, that can be extruded and they form some sort of composite where you can see the silicon oxide particle will be inside the polymer matrix. In case of solution blending, a solution blending will be made in a liquid form. So in liquid state, a powder will be processed and then they will mix to a little bit of more molecular level because it is in the solution form. And these nanoparticles will be actually incorporated inside the polymer particles. When you come from salt gel process, this is a very well-known common process, salt gel process. In salt gel process, basically there are two steps. The first step is the hydrolysis of the different metal alkoxide, which are used to form the final inorganic particle. And the second step is the polycondensation of these reactions, of this alcohol that we produce. However, critical is that on the right side schematic, if you look at it, if there is an active ingredient, for example, there is fragrance, inorganic, let's say corrosion inhibitor, some odor removal agent, or maybe some sort of other chemicals which we really want to have it inside a matrix. So you can have the active, you can stabilize in an emulsion, then a silicon precursor will be added to it. And finally, when there will be, stirring will be given, a lot of particles will come close together, they will hit each other, and they will actually have some sort of collision. And from that collision, once we had two ways to work, one is that you can add base, another is in case of addition of acid. In both cases, we have different morphology, but the active ingredients, whatever we are talking about, that will be coated on top of the silicon precursor, that is silicon oxide particle. And here also you can form a different type of morphology. But the beauty here is that if someone wants that, let's say here we're talking about silicon oxide core polymer cell. We can also design an opposite way, polymer core silicon oxide cell. We can also think about the polymer core silicon oxide cell, but later on the polymer is dissolved. And you can think about a hollow particle. This hollow particle can find application, different application, for example, sound absorbing. We can also load that later on with some sort of pharmaceutical ingredient and so on, which can be used for biomedical applications. So in one word, Salt Gel method is widely used to encapsulate different type of ingredients, either in silica matrix or the silica matrix contains the ingredient and further polymer is coated onto that. The other method, which is very common, is the polymerization method. In polymerization, I mean here that it could be emulsion, it could be milli-emulsion polymerization, it could be solution polymerization, or it could be dispersion polymerization. But mostly for encapsulation purpose, mini emulsion and emulsion polymerizations are widely used. But here there are some critical conditions. The condition one is that the inorganic silica particles that we would like to coat, that must be surface modified, because silica, these particles are very hydrophilic in nature. So the moment we put in water, they will be more or less like a dispersion, soluble type of dispersion. So to make it first hydrophobic, so that we can disperse it in water, and afterwards all the relevant steps will be conducted. And this functionalization is critical because that will actually have the base to form the polymer on top of that. Beside that, there are many other technology, but one of the technique, for example, you are familiar with, that is called layer by layer assembly technique. With this layer by layer assembly technique, there are also, for example, several layers. So give an example, let's say we have a cationic polymer. We can first deposit the polymer, inorganic particle will be taken, a cationic layer is deposited, then an anionic polymer layer can be deposited, and finally again a silicon oxide dispersion or any other inorganic metal oxide can be deposited, further cationic, anionic, or any other inorganic particles. So meaning is that you can actually build around silicon oxide. If we take an example, we can have 2, 3, 4, 5 layers of different polymers or composite of polymer and silicon. And that can be done in layer by layer deposition technique. However, that technique, commercialization of the technique is very crucial, and a large production may not be feasible there. Now I'll come to the emulsion polymerization. So I think that is the main polymerization technique which is actually used for encapsulation of inorganic particles, in this case silicon oxide particles. But before I move to the process, let me have very few basics concerning emulsion polymerization. So as we all are aware that in emulsion polymers, there are 4 ingredients. So one is ingredient means water, which is a solvent or the media. Then we are adding surfactant, monomer, initiator, we are stirring it, heating it to certain temperature, polymerization taking place, and we are ending up with the polymer particles. Now, if you look at the mechanism a little bit in a very simple format, so when we are adding surfactant in a system, so it is water, surfactant has both hydrophobic, hydrophilic, till we know that. But once they are in water, the obvious reason is that all the hydrophilic part will be towards water and the hydrophobic part will be outside water. So they will actually accommodate on the surface between water and air surface. Now, the moment we start stirring, we force them to go inside the water, which they do not like. In the sense, the hydrophobic part don't like to be there. So after a certain concentration, they will create some sort of hydrophobic zone and they will assemble to form some small aggregates which are called micelles, where you can see all hydrophobic part should be one side and hydrophilic part should be surrounding that hydrophobic part. Now, at this moment, what is in water? This is initiator. Then the initiator, when it is heated, it will form radical. So in water, there is radical, there is micelles, and now the monomer is added. So the moment the monomer is added, now the monomer is again, it's a oil, it's a hydrophobic material which will be stabilized by the surfactant again. But the monomer will actually move from the big droplet to these hydrophobic zones. The reason is because there is a high concentration here and there is low concentration here. So because there will be diffusion taking place, which will be via the water. So now after some time, what will have a monomer rich micelle. Now, initiator will be there in the water. The moment we heat it, they form the radical. This radical will come and they will react with the monomer. This time, a particle will be formed. The particle will be larger and larger. And at one point of time, the particle will be stabilized. They will separate from one particle. Then different reaction centers will create a large number of particles. All of them will be stabilized by the surfactant again. So these are known by all of us, but I want to mention because the next step that will be very critical to understand how we can conduct encapsulation using immersion polymerizations. Now here, if you look, there are a few critical stages. Critical stage, all the things what we talk about is water. Now the medium is water, initiator is water soluble, initiator is water soluble. Now my monomer is available in where? It is available in hydrophobic zone. The question is why initiator will go to the hydrophobic zone. So that is the critical stage which will determine how much polymer will form. Second step is once the initiator is inside this hydrophobic zone, they do not love this zone because they would like to come back to the water, which is a stable zone for them. They are soluble there. So the moment an initiator, that means a radical, enters to the particle, and then it stays there for some time, and it comes back. The longer it stays, the larger polymer chain will be making. The other part, these initiator. So if you look at the number of monomer, the number of centers, the micelles that we have created, and the amount of initiator available for the reaction, actually the chances of one monomer to get a radical is only 50%. So the meaning is that everywhere when we talk about the polymers which will be making, will be of different molecular size, particle size will be of different. So there are certain ways we can control that so that we can have very uniform molecular distribution of this polymer particle size distribution. We can create similar sort of particles. For example, you want to create particles, a different range of particles after some time. So during the process, if after 3 hours, I added a little bit of surfactant, they'll create new micelles. So particle will actually start building there again. In other way, the control is much more because these are semi-continuous system. It is starved condition in the sense I have water, I am adding surfactant, I am adding monomer. If I don't add initiator, the reaction will not take place. If I add surfactant, water, initiator, if I don't add monomer, the reaction will also not take place. So I have two ingredients, either monomer or initiator, which is in my control, and I can add it the way I like. But usually initiator concentration is very less. So people move to monomer because the concentration is more. So in a long run, 3-4 hours addition time, you can actually precisely control that. And always the reaction happens in the starved condition. If it is not starved condition, then the complete picture will be completely different. Now let me come back to the encapsulation point. Now what will happen here? So earlier you could see that water, initiator, monomer and surfactant. Now what we are doing, we are adding silica particles there in the beginning itself in the reactor. And we'll conduct the same polymerization, we'll heat, we'll add all the ingredients, whatever it is. And at the end, we'll have silica particles which are coated by polymers based on whichever monomer we decide. But the criticality here, that's why in the previous slide I took some time. If you see the picture, almost everything remains same. Only one factor which will play a role here. The role is now here, there is a competition between this. See that the monomers are in the micelles, the hydrophobic zone, but you also have silicon oxide particles. Now, when you have silicon oxide particles, question is monomer would love to go to the micelle or they would love to go to the particles, the silica particle, because if they go to the micelle, they will form free polymer particles. And if they go sit on the silica particle, then the polymer will be formed on top of the silica particles. So now the question is, how can you make or how can you force the monomers that they should prefer and they should go towards the silica particles and not to the free micelles? Because at the end of the day, when we conduct the reaction, our purpose is that whatever silica particles, whichever amount we have used, all of them should be coated. And if there is free polymer, the meaning is that a majority of the silica particles will remain as free. And I told you that in the beginning that silicon oxide particles, when it is used in the beginning, those are already modified. they are hydrophobic in nature, and then it is stabilized by surfactant, which are dispersed in the system. When you start with that, and there are many type of strategies can be play around. For example, if I want that polymerization should take place on top of silicon oxide only, in that case, I can do something. For example, I can think about a molecule, a species which are already pre-absorbed. For example, silicon oxide surface is already pre-absorbed by initiator, or maybe some surfactant I'll use where one part of that will act as a surfactant and remaining part will act as a initiator. So some sort of silicon oxide particle, if I modify it, as I said in the earlier, that if one of them are not available, the reaction will not take place. So if I bound all the initiator, for example, on the silica particle, then obviously the reaction will take place on that surface, and in most cases will be forming the polymer coated silica particles. Otherwise, to use different type of monomers, some sort of modification we can play with, and most critical is we can play with the surfactant, because when we are talking about the surfactant will be required by now two species. One is the micelles, the polymer particles which are forming, they need surfactant to be stabilized. At the same time, the silicon oxide particles which are also coated by polymer, those also need surfactant. And this balance, if you can play with it, there is always a balance, and in that balance, we can reach up to a level, I mean to say nearly 85–90% of the silicon oxide particle can be coated by polymer. And when people are using mini emulsion or other dispersion polymerization, they can actually even reach to a level of, I should say 98%, 99% of the encapsulation efficiency they can reach. And there are many strategies, as one of them is initiator, another could be surfactant, another means all the species. What you have to do, we have to play with the mechanism in a way that we are not, the system is not allowing the polymer particles to form. Rather than everything, everybody is interested on the monomer which are sitting on the inorganic particle, silica oxide particle, and they are there reacting with. Now, based on the polymer that we are using, hello.
Yeah, sorry to interrupt. 4 more minutes, please.
So then the polymer that whatever using, the morphology depends on the type of polymer. For example, if I use PMMA, we can have a very smooth cell around the polymer. If I use polystyrene, then they will form some sort of necklace type of structure on the silica particles. And if I use cross-linking, then this type of polymer again will form a smooth layer on the silica oxide particles. So depending on the type of monomer, depending on type of the cross-linking agent, the morphology can be played with. And based on the morphology, the final properties also can be varied. So now there is an application slide. So I think this slide talks about application of silicon oxide particles, silica layers, silica coatings in different type of coating applications. The market is also presented here, but as I have 3 minutes time, I'll not go through that. I'll only talk about one example. So for example, BASF has a product which is they are selling acrylate polymer which is silica coated and having the raspberry structure which is widely used for easy clean self-cleaning purposes on the paint industry. Now for the different challenges, one challenge is product cost, because if I have silicon oxide today and if I want to make it encapsulated, obviously my cost will increase. The other one is compatibility with the organic matrix. I'm saying here the compatibility, the reason is that directly the silicon oxide particle, if I had to do some modification first, different type of coupling agent, some reaction has to take place, some silanization can be done. And then finally, if I made it, they will be much more compatible to the organic matrix. Then process criticality. Process criticality is very important. For example, in the slide what I was explaining, and there if you look at it, if I have 4 ingredients and one of the ingredients is not compatible, then at one point it will happen that the complete batch will gel. To give you an example, only to incorporate 0.6% of silica in an emulsion polymerization, somebody using a silane, and if that is not added properly, the whole batch will gel. So process is very, very critical. Then obviously homogeneous distribution of SiO2 particle is also very critical. Otherwise, you don't get the advantage of this silicon oxide particle. Then I think when I joined the seminar, I found that people were talking about making silica from rice husk, and that part already discussed with them. So what I was talking about that sometimes silica might be biocompatible, they may have low toxicity or no toxicity. However, the process which they are made, that may be having some hazardous chemicals. Control on morphology. The morphology we want to have, we have to make sure that we are having majority of the particles in that morphology. Then the other concern area is the loading of the silicon oxide. For example, if you are thinking about that, you will be loading higher amount of silicon oxide, then the overall matrix will be very hard, and then there will be crack in the film, or maybe all the mechanical properties other will be decreased. So it is very critical that how much amount of silicon oxide we can add, and based on that we can also see which level of properties that we are expecting from that composite particle. Then my concluding remarks is that this type of polymer composite can bring the benefits of both the world, and sometimes the contradictory properties can be balanced. For example, I am looking in one hand that my system should be very hard. On the other hand, I am thinking that it should also be very flexible. And then the other part, you can also think about different type of ingredients. For example, a lot of ingredients can be encapsulated using this silicon oxide approach, and those can be used for slow or low leaching, low release applications. And this type of, especially silicon oxide, is known and famous for its cleanability. And somebody already gave an example that it also offers very good antibacterial effect as well. So such applications it can be used. And for its because of its biocompatibility, a different type of biomedical applications, this can also be used. And recently, if you look at the number of patents, publications, and also small companies, small startups which are coming up, you could see all of them are on range. That's all from my side. Thank you so much. If you have any question, please let me know. Else you can move to the next presentation.
Yeah. Thank you, Dr. Sopan, for your detailed discussions on the basics of silica incorporated polymeric materials, application, and its associated challenges. We may have one or two questions quickly. There is.
Dr. Swapan, I mean, are there any kind of what do you call relationship made between the nature of silica and the nature of polymer before, I mean, making a kind of a composite? Is there any kind of a priori methodologies or chosen? What kind of a silica can be basically coated on what kind of a polymers or incorporated?
So for example, it all depends. When you are focusing specifically on types of morphology, then actually it depends on the surface energy of the surface. So we can have different level. For example, silica surface, a specific contact angle we have. Polymer, we have a specific surface tension. So this surface tension, based on that differences, you can already pre-predict which type of morphology we would like to have. Now coming back, if you are not looking at specific morphology, it's just a simple core cell type of morphology. In that case, it all depends what are the surface groups on the silicon oxide particle. And based on the polymer, the monomer that you would like to incorporate there, that compatibility you have to see. And if it is not available, it can be modified and afterwards can be used for polymerizations.
Thank you.
Thank you, Dr. Sopan.
So much.
Yeah. Can you please answer your slides so that we can go to the next speaker?
Trying to do that. Somehow I don't know why it is not working. Maybe the other speaker can start sharing that it will go automatically.
I think it will be possible. Let me try.
Some issue, I don't know.
Yes, I think only if you answer, then we can proceed further for the next presentation.
I am doing it, but yes, now it is answered. No, it is done.
Thank you. Yes, done. Thank you.
Thank you so much.
Thank you for your time and for your detailed discussion. Thank you. Now, we move on to our next invited speaker, Dr. Bijan Roy, who joined us today in person. Thank you, sir, for coming CSIR, CSMCRI. Dr. Bijan received his PhD from the Indian Institute of Technology, Kanpur, and he did his postdoctoral research in the same institute. He has vast experience in diverse industries. Initially, he worked as an in charge of analytical and chemical division in Hasteri. Then he moved to Apollo Tyres Limited, Vadodara, and he worked there for almost 10 years. Later, he joined as General Manager, R&D and Technical Services in Philips Carbon Black Limited. And presently, Dr. Bijan heading the R&D and Technical Services in Madhu Silica, Bhavnagar. He has several research papers in internationally peer-reviewed journals to his credit and an inventor of patent. He has been associated with various professional bodies, institutes like American Chemical Society, Indian Chemical Society, Indian Societies of Analytical Science, Indian Thermal Analysis, or a few of worth mentioning. With this brief introduction, I request Dr. Bijan to deliver a talk on precipitated silica for tire and rubber applications. Dr. Bijan, please.
Good afternoon, everyone. Today I'm here to talk to you about precipitated silica, its technology, applications, and performance in rubber compounds. My presentation is split into 4 key areas. Firstly, I will talk about precipitated silica applications and its rubber compound properties. So in precipitated silica, since I am talking about the precipitated silica in rubber and tire compounds, first of all, we should understand what is the silica for rubber and tire industries. So mainly the silica, precipitated silica is being used in rubber for a reinforcing filler. Primary application of this precipitated silica as a reinforcing filler. So if we look at the filler classification in rubber and tire technology, so only it is based on the primary particle size. Normally smaller is better is considered for high reinforcing fillers. So you can look at this chart. The smaller the particle in the tune of below 100 micro or 100 nanometer are considered as the reinforcing filler. So in terms of rubber and tire industries or any kind of rubber industries, precipitated silica is being used as a reinforcing filler. It is a white filler, and the other filler, which is the reinforcing, is the carbon black. So these two fillers are the primary fillers for any rubber compounding for making tires and finally any rubber products. Now, this precipitated silica, if we look at the main classification, it is a silica only. The chemical it is SiO2 only. So SiO2 can be classified as either it is an amorphous silica or it is a crystalline silica. When we talk about the amorphous silica, because our precipitated silica comes under this amorphous silica, it is synthetically made. So synthetically made amorphous silica again can be classified into 2 major categories. One is the pyrogenic silica, or we call it fumed silica, and the other is precipitated silica. And Silica Gel is a part of that precipitated silica category. And after this precipitated silica manufacturing process, if we do some treatment of that particular product, silica, it is called surface treated silica. So basically, precipitated silica, what I am going to talk about is the synthetically made amorphous silica precipitated out in aqueous medium in the wet process. Now, if you look at the applications, end-use applications, specific silica is useful in myriad of applications. Every day, everywhere we go, and virtually everything we do, we find products that would be unthinkable without using silica. It starts early in the morning in the bathroom itself, when we brush our teeth by using toothpaste. That toothpaste, it contains silica, and the purpose of the silica is to control the rheology. It is how the toothpaste is flows about or flows out of the tube. And another function of this silica in the toothpaste is how effectively it cleans our teeth. So there are two kinds of applications in the toothpaste. One is the rheology control, and the other is your cleaning purpose. Now coming about this, at the breakfast table, we are using cappuccino, coffee powder, salt, spices. So it ensures, this silica, it ensures free flowability of this particular material, this particular your breakfast table meeting items, because it restricts the formation of cake. So here silica is being used as an anti-caking agent. Now when we talk about the printing paper, the fifth nature of this printing paper is due to the presence of a special kind of filler, silica filler. Even if we are in cars, battery separator, battery car used in the car, the separator used is made up of silica. Because of its porosity, this silica acts as it permits the flow of electrolyte, but it restricts the connection between the anode and cathode. In mobile, you're using silica in a silicon rubber compound in the keypad and all these things. So it has got a myriad of applications. Since my presentation topic is restricted to rubber and rubber-related tire compounds, so I will talk about now my parts, that is the tire and rubber compounds. So the function of silica is different for different applications. As I said, when we use toothpaste, it is used as a cleaning agent or rheology control. When we use in the cappuccino powder, coffee powder, or any spices, it is used as an anti-caking agent. When it is used in a polyethylene film, it is used as an anti-blocking agent. So purpose or function is different for different applications. Now our discussions is limited to tire applications. So in tire, silica is being used. The functional requirement of a tire is to get the high reinforcing. It has got a high tear and cut growth resistance. It requires a very good or quality of adhesion between, because in a tire you see there are rubber, there are chemicals, there are metal, fabrics. So adhesion between the metal and rubber, these are requirement of a functionality of a tire. Similarly, the recent discussions are based on the rolling resistance, which is directly related to fuel efficiency. So rolling resistance and weight grip, and another part, that is the safety of the tire. So weight grips means it gives an indirect process to measure the how safe the tire is. So all these functional requirements are required for a tire, and silica plays an important role to fulfill all these functional requirements of a tire. Now, as I said, as I showed you that in the previous slides, that in rubber and tires, there are two reinforcing fillers only. One is silica, the silica is the white filler, and the other one is the black filler. Now, since the functional requirement or the recent requirement of a tire is to get minimum rolling resistance, that is high fuel efficiency in terms of environmental function, less carbon footprint. So rolling resistance and weight grip, that is the safety. Silica, due to its inherent property, it gives a better rolling resistance. It gives a better or high weight grip properties. So it is an inherent property. If you compare with the carbon black, and the property is measured by some dynamic mechanical analyzer. So tan delta is a factor by which we can measure the 60° centigrade tan delta. It is lower. The lower is better for rolling, higher, low rolling resistance, and tan delta at 0° centigrade, which is higher for silicon compound. So it gives a better safety, that is the weight grip properties. So since there are two fillers, reinforcing filler, carbon black and silica. So in terms of when you're using a tire compound with silica-based compound, it gives better rolling resistance. It gives higher safety, that is the weight grip properties, due to its inherent silicon characteristics. Now, if you look at the difference, because these are the two fillers, nano fillers, primary particles based on nano fillers. These two fillers, if you look at the difference in the aggregate scale, you will not find any difference between these two. On an aggregate scale, silica and carbon black have a similar appearance. So this is the ACM picture. So you will not differentiate between this silica and carbon black. But when you look at the atomic scale, you will find that silica particle is surrounded by many inorganic functional groups, whereas the carbon black particle are surrounded by many organic functional groups like lactone, ethylene, keto group, or hydroxyl group. So atomic scale only you can differentiate between the silica and carbon black, but not in the aggregate scale. Aggregate scale you will see the similar behavior. Now, due to these differences of carbon black and silica, with silica compounding, it gives a higher viscosity, the rate of cure will be slower, lower crosslink density, and these are the properties to be achieved with silicon compound. But again, when we're talking about silicon compound in rubber, because in rubber there are basically 3-4 types of rubber, like your synthetic butadiene rubber or butadiene rubber or natural rubber are mostly used in tire. So silica, being polar in nature, is not that much compatible with the polymer itself. So when we're using silica in higher dosages, then silica, there is an another requirement called sealant coupling agent is required to mix all the silica into the rubber matrix. So with silicon sealant system, the all properties, the requirement of the properties will be achieved. That is high resilience, hysteresis, low hysteresis, and better adhesion. That is the better durability of the tire. Now we are representing Modusilica. Modusilica is well diversified, having well diversified product portfolio. If you look at this product table, you can see that we have a different grades of silica, starting from the part surface area as low as 50, 55 to as high as 300 meters per gram. So based on this surface area, we classify different grades of silica, which gives different product properties of particular tire compound. And again, there is a classification of, since as I said that silica being polar in nature is not that much compatible like carbon black. So it is dispersion of silica, especially with higher dosages, are difficult. So continuous research is on to identify the how to develop newer silica grade which will result in better dispersion. That is, that way it can be silica. We classified silica, we developed silica, we are marketing silica in a different category. It's called the conventional silica, that is the regular silica, semi-dispersible silica, and the high dispersible silica. Now, if if you look at, I will show you the manufacturing process. If you look at the silica, it comes as a powder first. So there are three physical forms exist in any silica manufacturing company. The physical form is either in the powder form, and the another is the granular form, small granules. And the third one, which is really gaining momentum and recently using more industries are using this microparticle. We are calling it the free flow silica. That is the dust-free silica, because if the silica is being used in the shop floor, it has got a very high dust, it's producing a dust in the shop floor. So dust-free silica, there is another physical form where the controlled particle size are maintained. So we have three different type of silica in three different physical form. Either it is powder, granular, or dust-free. Now coming to my second part of presentation, that is the differences in product properties. So conventional silica, there is the regular silica, and this is the high dispersible silica. If you look at the differences between this, because in my first slide, I showed you that it is a silica molecule only, SiO2 only. Chemically, it is always SiO2. But we can produce silica with different gates having different morphology. So this leads to different kind of products under this category, conventional or highly dispersible, or in between there is a semi-highly dispersible also. So if you look at the difference between the conventional and the highly dispersible silica, and highly dispersible means it is dispersed well in the rubber matrix. So these are the main major properties which plays an important role in the dispersion of silica in rubber matrix. The structure, that is CDVP, there is now DVP is replaced by DOA, there is diopter adipate absorptions. Porosity, that is measured by mercury porosity. WK coefficient, that is measured through particle size analyzer. Sears number, that is the surface chemistry of silica, and overall it leads to lower size in the dispersed phase in the particle size of the rubber matrix, and this is the size of the particles are lower in the highly dispersed silica. Now I just show you 2-3 slides. It is a comparison between the regular silica and the highly dispersible silica. If you look at the compound properties, the end product property, dispersion is a dispersion. It shows the dispersion is better. Muni viscosity, it actually dictates how we process the compound. So lower the Muni viscosity, it will be better processed. So with the highly dispersible silica, always it gives a lower Muni viscosity. And in terms of curing, that is in terms of production, highly dispersible silica and regular silica are comparable. But the processing point of view, the dispersion point of view, and ultimately the product mechanical properties like your heat buildup or wear properties are always better with highly dispersible silica. The same is true for physical properties, that is the modulus, tensile strength, and elongation break. Dynamic properties, as I said, that this is a requirement, is a mandatory requirement. All European countries are taking only tires with having low rolling resistance, that is the 10 delta at 60 degrees centigrade. The lower the 10 delta at 60 degrees centigrade, better is the rolling resistance, or better is the fuel capacity, fuel efficiency. So with the highly dispersible silica, you will achieve better fuel efficiency at better or higher grip, that is the safety of the tire, as well as the modulus will be better for highly dispersible silica. Now coming to the third part of my presentation, that is the chemistry and product characterization. It is known that silica, it is the manufacturing process, it is prepared through sand and soda ash at high temperature, around 1400 degrees centigrade. So sodium silicate is being formed in the solid form. These are called cullates. These cullates are then melted in a vessel, or it is a liquefaction process. So sodium silicate in a liquid form, along with the acid, it is the normal silica acid-based triturations, and silica is being precipitated out. So the first step is the reaction. Second step is the filtration. and third step is the drying. The first step where this silica is being precipitated out, it is in the tune of 8 to 10% only, or even 5 to 8% only, to be very precise. After this, and the rest is your water and the byproduct sodium sulfate. After filtration, when the filter K is formed, the water content is around 80%, only 20% is solid. And when we dry it, then this water is driven off and we get the pure silica. So categorically, there are 3 steps, 3 unit operations. One is precipitation, the second one is filtration and washing, and the third one is the drying. Now, as this, among these 3 steps, the primary or the major important step is the reaction. After the reactor stage only, you can control the particle size, you can control the structure, you can control your primary surface functional growth, and all these properties. So 80% of the product, final product, is governed by the reaction itself. So reaction is the heart of precipitated silica properties. So in the primary stage, when it is formed, is the primary particle, but it is very unstable. Immediately it goes to the aggregate, and ultimately silica being due to hydrogen bonding, it actually is formed in the aggregate. So control of concept of silica growing process in the reactions is the major characterizing role in silica. Now in tire, these are the 3 important parameters one need to achieve, otherwise a tire cannot run in the field. One is the fuel efficiency, and another is the wear resistance, and the distraction. Distraction means your safety. Fuel efficiency means your resistance, loading resistance should be low, and wear resistance good means the tire should be durable. It should run for a longer period, say 50,000 kilometers, even 1 lakh kilometers. So these are the 3 major properties which are the requirement of a tire, and these 3 properties can be translated for silica, how to control these properties by means of surface area particle size, by means of its surface activity, or the morphology and porosity. The key property is the surface area. We have 2 types of surface area. One is the BAT nitrogen surface area, and the other is C-type surface area. BAT, it is a nitrogen being a smaller molecule. It can penetrate inside the pores. So it is a higher surface area altogether. But C-type molecule is a cetyl triethyl ammonium bromide. It is a bigger molecule, so it cannot penetrate into the pores. So it is only the surface area can be measured with the C-type. So rubber, since it is a bigger molecule polymer, so C-type surface area is a major parameter that can be characterized in addition to the BAT surface area. Again, the morphology, porosity, how the porosity, better the porosity, better will be the dispersion of silica. So it gives a very, this Marconi porosity is a very important tool to find out the properties of precipitated silica. Now, I'll show you this graph. This is the conventional kind of silica where you can see the broadness or peak sharpness. This is a sharp peak. For highest possible, the peak is broadened and it is extended. So polymer being a higher molecule, you need your silica should to be porous, and the pore size distribution should be it has got a very high pore size distribution like this. This is a single absorption. It is a monomer kind of silica. But when you talk about this highly dispersible silica, we require this much of broadness of porosity. So pore size distribution plays an important role, and Marconi porosity is the machine or instrument by which we can measure all the pore size distribution, the pore size, average pore size, and different calculations there. Another very important parameter of silica is its particle size. whatever we are producing silica in the final form, it is in the aggregate form only, not the primary particle size. But that aggregates, when allowed to mix in the rubber matrix, it disintegrates. It disintegrates into smaller fractions. So when you measure the particle size of silica, you can see this chart. This is the standard silica, the red one, and this is the highly dispersible silica. So here is the volume distribution, and here is the size. So if we scan these two silica, we will find for highly dispersible silica, it is a bimodal distribution, and the particle size, because you need to apply some phonography or some shearing force in order to measure this particle size. It is a standard method. So particle size when you measure, it is just synchronizing when silica is being mixed into the rubber in a galvanic mixer, because there is a shearing force by which the silica particles can be disintegrated. So here we simulate this process. Silica under this phonography, it has disintegrated. So higher the disintegration, it is a higher molecule. So higher the disintegration, that means lower the particle size, better will be the dispersibility of that particular silica. So that way you can see in the rubber mixed compound for standard silica, you can see different spots. This white spot means silica and this spot silica. But when you see these highly dispersible silica, rubber compounds, the black compound, you will not even find any white spot. So it is a very highly dispersible. Another morphology which plays an important role for this highly dispersible silica is the DOA or DVP absorption, which is directly related to the structure. Better the higher the structure, better will be the dispersion. Now, just there, I have covered up two subjects. That is, one is the morphology, and the other is the surface area of particle size. Now, the interface, the structure, silica is being formed, but since it is the structure where its surface is surrounded by different functional groups, so the interface chemistry is very important for silica and its performance in rubber compounds. As we know that silica is having two kinds of moisture. One is physically bound moisture that can be driven off by heating only at 105 degrees centigrade for 2 hours. We call it loss on drying. And chemically bound moisture in the form of surface silanol group. There is a hydroxyl group. All the hydroxyl groups are there. That cannot be driven off by 105 degrees centigrade. That can be only removed by heating silica at 1000 degrees centigrade for 2 hours. So if you look at the TGA graph, you can see that the silica, it is a higher the temperature, when 200 and more, the functional OH group, which is chemically bound, that is driven off. And this moisture loss is only heating moisture, that is only attached with the surface. It can be easily removed, but not this molecule, this water molecule. So surface area of silica or the surface of silica is surrounded by hydroxyl group. And these hydroxyl groups has different positions called vicinal group or geminal group or kind of isolated group. Depending on the concentration of this hydroxyl group, the functionality of silica in rubber, it plays a role. So that can also be measured, how much quantitatively, how much silanol group is there, how much the fraction, whether it is geminal mode or whether it is isolated mode. And so interface, we measure some Sears number, we call it Sears number, by which it gives an accurate figure of how much hydroxyl groups is present in the silica and what is the requirement of the functional groups. Because as I said, that when silica is used in more proportion, that is the loading of silica in any particular compound, in rubber compound is higher. Not only silica, you need to add some sealant coupling agent as well. So sealant, in other terms, when we use carbon black on no silica, there is only a mixing, physical mixing. But when you use silica along with sealant coupling agent, there is a reactor, there is a reaction. So in reaction, this moisture, as I said, this moisture, that is liquid moisture, is very much essential to have this selenization reaction. That moisture acts as a catalyst. Now this is a figure of it is a functional group because isolated group how much hydroxyl group is presented as an isolated form, how much is a geminal form, or how much is a functional form. Now I come to my last slide conclusions that even though silica is widely used or popularly gaining its interest or everywhere the dosages or usage of silica is gaining more and more, but it has got many challenges. First of all, dispersion, and this dispersion is due to the incompatibility between polarity because silica is polar, where the rubber compounds or the rubber, especially polymers, are non-polar. So the dispersion or distribution of silica is a challenge. Compound stability, since silica is surrounded by hydroxyl group, many hydrogen bonding are taking place. So agglomeration, re-agglomeration of silica, that is called flocculation in terms of rubber technology. So it is a very, it is a product, is a disadvantage of using silica because when you mix a silica compound and keep it for 2 hours, 3 hours, and then again you have to process it, then it becomes a very hard for we harness. So that is another challenge, and obviously the compatibility. So having said this, present condition silica is being used everywhere, but the scenario due to our market structure, due to the legal requirement, due to the environmental requirement, today silica and tomorrow silica will be using. With this, I come to my conclusion.
Regarding the CTF surface areas, can you get some idea from the nitrogen PET surface area considering the external surface area? The pH profile distribution.
As I said, because this surface area is measured in terms of all the principle is absorption. Okay, so nitrogen molecule is a smaller molecule because silica is a porous in nature. So it has got pores on the surface, it has got pores inside of it. So nitrogen molecule can easily penetrate or absorb on the surface as well as it can enter into the pores. Whereas CTF molecule is a bigger molecule, it cannot enter the pores, inside pores. It only absorbs on the surface. So you will always get CTF surface area lower compared to the nitrogen surface area. And this difference between the PET surface area, nitrogen surface area, and CTF is your microporosity. And that microporosity is measured by the 80%. So you need to create the porosity for better rubber mixing. Yeah.
Yeah. Thank you, Dr. Vijan, for your detailed discussions about different grades of silica, and even you have pinpointed some special properties of silica and how it differs from carbon black for its diverse applications. Thank you very much for enlightening us about silica-based products. Thank you. Now we are moving to our last invited speaker, Dr. Dhananjay Sabde. Sir, can you please load your presentation?
Yeah, I'm yeah. Is it visible?
Yes. Can you please make it in slide share mode?
Yeah, just 1 minute. Oh.
So, Dr. Sabde received his PhD from the University of Pune in association with CSIR National Chemical Laboratory. Then he moved to his postdoctoral research in University of Reims, France, and then successively to Leipzig University, Germany. Then he was the head of R&D of Madhu Silica Private Limited, Bhavnagar, for the period of 2005 to 2007. Then he moved to Sudhkami India Private Limited, Baroda, and served in different designations. Presently, he is the Chief Manager, Research and Development, Sudhkami India Limited, Baroda. He has vast experience in the development of inorganic materials for its application in adsorption and catalysis. To his credit, he has good number of international publications and 7 patents. With this brief introduction, I request Dr. Sabde to deliver a talk on applications of silica in catalysts and adsorbers. Dr. Sabde, please.
Yeah, good afternoon. Thank you, Dr. Saravanan. I'm audible?
Yes,
I'm
sir.
audible?
Yes, yes.
Sir, you're audible.
So, thanks for the kind introduction. In fact, I will take this opportunity to thank this organizing committee of IMPS 2022, Dr. Saravanan, Dr. Ankush, Dr. Subramaniam, Dr. Kannan for this opportunity to be before you to share some of my experiences related to silica, going into different applications in zeolites, making of catalyst and adsorbent. One minute. Yeah. So is this slide visible?
Yes, sir.
Okay. Now, before going to the main topic of the today's talk, I will just like to brief about our company. Basically, if you see Sood Chemi India Private Limited, it was established in 1969 at our Cochin, Kerala. Subsequently, after 10 years, somewhere around 78, the second unit came into existence at Nandesari, Baroda and Gujarat. In 2011, Sood Chemi was taken over by Clariant. Basically, if you see, Sood Chemi is a JV with Clariant as far as this Indian counterpart is concerned, and we are basically a part of Clariant Group. Now, Sood Chemi India Private Limited, basically, many of you know that we are into making of catalyst and adsorbents, which are going into different applications. Now, if you see the different type of applications wherein we are, one is the fertilizer industry. As you know, in fertilizer, urea is the final product. To make it, the process starts with, an hydrocarbon purifying, then going to the steam reforming, then subsequently, shift catalyst, and getting hydrogen, and from hydrogen we go to ammonia, and then subsequently this ammonia is basically converted to urea. So this is basically one industry type wherein we are into making of adsorbents and catalysts. So when we talk about the other industry type is basically refinery. In refinery also actually we are into making of adsorbents and catalysts which are going into different applications. One of them is basically we are into making of FCC additives, which normally we say that FCC is basically a heart of a refinery. And basically we are making into the FCC additive catalyst for that. We also make hydrotating catalyst. We also make isomerization catalyst. We also are into making of different catalysts for petrochemical applications, which we talk about selective hydrogenation, or maybe methanol to propylene, or maybe ethyl benzene to styrene. Basically, it is nothing but the value addition of the products of a refinery, which normally in the petrochemicals we take care. There's another business area where we are into is air purification. So as you know, I meant to say air purification in the coming years has gained a lot of importance because of several reasons, as it is directly affecting the health of everyone. So we are also into making of catalyst. Normally we mention that as catalytic converters, which goes into two-wheelers, four-wheeler applications, wherein it caters to converting this harmful exhaust emissions into less harmful, or maybe we can say some gases which are very less harmful to the environment and health. Now we are also into making of fine and specialty chemicals. Just to give a couple of examples, like we are into development of catalyst. We have developed a couple of catalysts for different fine chemical applications. I can give just example like we have developed catalyst for this thymol, which starts with from a metacresol alkylation with propanol. This is basically an intermediate to menthol. So we supply this on a commercial scale. The other intermediate which goes into making of vanillin is basically guaiacol. So we are also develop a lot of catalyst for guaiacol and many other alkylation, acylation type of applications. So this is basically our fine and specialty chemicals portfolio. We are also into making of different aluminas. See, as you know, I mean to say, if you see major of our catalyst, alumina is the main constituent. Silica, yes, but to very small extent. So to have a self-reliance on this alumina, we were earlier actually dependent on third parties or maybe these were being imported. So recently, actually, we have gone very strong and developed whatever is required for our own applications. We don't sell these aluminas, but basically these are consumed for our own applications. And in addition, actually, we are also into making of different types of zeolites, which are going into different applications, silico-aluminophosphates, and molecular fuse-based adsorbents, going into different applications. So if you see, like most of these catalysts and adsorbents, they come into different shapes, different sizes. So depending on the kind of technology the customer is using, maybe I mean to say. Accordingly, I mean to say the catalyst or an adsorbent is supplied. That may be in the form of a tablet, that may be in the form of rings, or maybe rigged, or maybe multi-hole. Extrusions, maybe the extrusions can be plain, CDS, bilobe, trilobe, quadrilobe, and also in the form of spheres. So this is basically some introduction about Sud Chemi. Now, couple of people talked about different silicas for different applications. I think I mean to say if you see from the perspective of our industry, wherein we make catalyst and adsorbent, basically there are a couple of silicas which we use in our applications. So those are basically precipitated silicas, Silica Salt, Silica Gels, pyrogenic silicas, or Alkoxy Silicates. These are basically for our interest. Now, when we talk about the first grade, which normally I mean to say we use, is basically precipitated silica. I think Dr. Rai actually very well mentioned how it is made and the type of applications it goes into. A wide variety of applications actually it has. So I just listed a couple of things, but I don't want to say to discuss more on that. What is most interesting actually to note is this global precipitated silica market, which presently is somewhere around 1.9 to 2 billion as of today, which is expected to to reach to approximately 4 billion by 2028. And of course, the major driver, as Dr. Roy mentioned, basically the kind of tires which are coming up with high-end tires, where the fuel consumption and all, I mean to say, it will be taken care by the development of silicas, which are going into specific tire applications. I mean to say those applications will drive this demand, and this kind of growth. Actually, what we expect is from that kind of an application. Now, coming to the another type of silica, what we use is basically pyrogenic, or typically we say as a fume silica. When we compare that with this precipitated silica, the fume silica they are very much low density material, like 100 to 100 grams may it may contribute to 1 liter volume. Basically, these also find applications in some of our developmental or a catalyst and adsorbent works. So when you compare the differences with respect to this precipitated silica, of course I meant to say in precipitated silica some amount of sodium sulfate remains. Sometimes that limits the applications for that. But in pyrogenic silica, this is a highly pure grade wherein you can expect the soda levels very, very limited. And in some niche applications, definitely I mean to say pyrogenic silica finds application. Now, the other applications basically I've just mentioned here, as a thickening agent, anti-caking agent, goes into cosmetics, silicone elastomer, viscosity modifier. But to some extent, yes, I mean to say these silicas are also used in preparation of, zeolite catalyst. The market forecast for, this pyrogenic silica, basically, if you consider, presently it is 1.3 billion USD, which is, poised to increase to 1.6 billion by 2026. And basically the drivers for this growth, which is expected from the fields like building and construction, electrical, electronics, automotive, transportation, personal care, food, beverages, and pharmaceutical applications. Now, the other grade of silica which we use is basically a silica salt, or normally we can say as a colloidal silica, wherein these are available in the liquid forms, and mostly these go into the our applications as a binder or a source of silica for making zeolite materials. Now, these also have different applications, they are used in surface treatment of paper, polishing agent in the electronic industry, also used in as an additive in varnishes, coatings, additives again in cosmetic applications. And again, if you see like what is the global forecast for this is presently actually in 2022 it is estimated to 1,000 US dollar million, which is expected to increase by approximately 25% by 2028. And again, I mean to say the drivers, if you see, is basically it is used as a polishing agent in semiconductor industry, and there are some niche specialty applications which is also a driver for this increase in projected demand for the silica salts. Now, this is another type of silica. Basically, it is a silica gel. So now this is very commonly known as desiccant silica. It's a drying agent, typically you can say, which is available in the form of small clear bits or irregular clusters. And of course, as we know, all like small packets, which includes these silica gels, are placed in this packing material. It can be any product. Basically, I mean to say that is used basically to avoid the damage because of the moisture to cater to that requirement. Actually, the silica gel basically they are used. So here again, I mean to say, if you see the global demand, basically it is presently at 560 million, and is expected again to reach 746 million USD in 2030. So the major applications what we see is again in the pharma sector, the packaging industry, wherein the growth is expected in the next decade or so. So this is another class of silica compound that we also use is basically alkoxy silicates. That is nothing but most commonly alkoxy silicates. What we know is tetraethyl orthosilicate, or maybe the polymeric form of this tetraethyl orthosilicates. So if you see, I meant to say these are basically colorless liquids. A normal tetraethyl orthosilicate will have 28% of silica in the alkoxide. And if it is polymerized to some extent, then there is a possibility that the silica content it can be increased to 40%. And again, I mean to say it will be in the form of an alkoxy silicate. So this is also one of the important raw material for one of our catalysts. So for the other applications, if you see for the alkoxy silicates, basically into precision casting, basically into the mold release agents. Then they are also used in inorganic binders for coating. Architectural restorations is also one of the areas where it is being used. Then also it is used in reinforcement of the concrete structures, additives in polymers. As Dr. Ghosh mentioned, like silica coated, polymers, they also find, different applications. So we can consider one of those type of applications here. And again, if you see the kind of forecast for this alkoxy silicate, it is just mentioned only for the ethyl polysilicate. It is not considered, any other polysilicate. It is again, I mean to say US dollar 284 million, which is expected to increase to 450 by 2032. And of course, I mean to say the drivers for the growth, which is expected from paints, coatings, and other industries. Now coming to the main, topic of today's discussion basically is silica, which is into zeolites, catalysts, and solvent. Now the common silica sources, what is used in our industry, is basically alkali silicates. There are different alkali silicates which we know: sodium silicate, potassium silicate, calcium silicate, etc. But most common what we use is basically sodium silicate. We also use the other silicas, what we mentioned: precipitated silica, pyrogen silica, silica salt, or even the alkoxy silicates. Now, where actually the applications are there for these type of silicas, if you see what kind of functions actually they work into the industry type, our industry type. If you see that the silica goes into making of zeolites and moleculars use, or maybe silica alumina based catalyst. Again, catalyst and catalyst supports basically they are employed. Again, I mean to say binder applications. Yes, I mean to say some of these grades they are used also as a binder, and some of the silica grades are also used as for pore regulation or surface modification of some of the catalysts. So I'll just give one example of each of them, so that just to give a clarity on the matter. Now, coming to the silica salt, like which is actually used as a binder in the catalyst manufacture. So this one application is basically it is one of the ingredients into making of this FCC catalyst or additives. So before going to this, I just want to mention what is an FCC is one of the unit operations in refinery. Basically, it is considered as the heart of a refinery. The reason is basically in a refinery we get the crude oil, and after purification and separation of different hydrocarbons, we get a lot of heavier hydrocarbons which remains, and a value addition is required for those heavy hydrocarbons. So basically, this is a process wherein this value addition is done, and that is nothing but the FCC process, that is fluid catalytic cracking. But basically, it is a cracking of the heavier hydrocarbons into smaller hydrocarbons, which goes into different pools. It can be it goes into either I mean to say LPG, gaseous these things, or maybe into lower hydrocarbons in a gasoline, or maybe in the diesel range. So the most important thing is basically, as it is a fluidized application, the most important thing is actually the density and the particle size of the FCC particles. So basically, I mean to say this FCC additives normally we mention is basically those are the spray dried products, wherein if you see the average particle size, it's somewhere around 70 microns. And what is important for the application is basically it should have a better a binding power, so that there is a lower breakdown, and the stability of the catalyst remains intact. So if you see the matrix of this FCC particle, there are a couple of constituents which make this FCC additive, or maybe FCC catalyst in general. So basically, one part is zeolite, the other is clay, there's a third constituent is alumina, and the next is basically silica. And normally when we are mentioning about silica, it is nothing but the silica salt. So also, I meant to say silica comes from zeolite, silica comes from clay, and there is a dedicated source for even for the silica, which is coming from the silica salt. Now, if you see what kind of properties normally these binders they have, is basically the silica salt, the particle size, it can vary anywhere from 2 to 150 nanometers. The distribution also varies. Normally, I mean to say, it's a narrow distribution, medium, or a wide distribution. even the silica salt, the silica content in the salt may vary anywhere from 70 to 50%. The pH also can vary from 2 to 12. Okay, and basically all these salts are basically stabilized, as we all know. And I mean to say the stabilizations come from either the ammonium stabilized or sodium stabilized. There are also some silicas wherein it is also stabilized by aluminum. So if you see, I mean, there's an image just included here is basically when we look at the different type of silica salts available in the market. So you can see, I mean to say there are some salts which are very, very clear and some salts which have a milky appearance. So this is basically a visual indication, like if the silica salts are maybe colorless, basically we can consider the particle diameter is it is less than 50 nanometers. And as the size increases beyond 50 nanometers, then I mean to say the silica salt is basically becomes milky, and these are basically different drivers wherein to optimize the properties of the particular catalyst. I mean to say a suitable version of this is used. Mainly I mean to say it will depend on the kind of application and the kind of desired properties which we want into the catalyst particle or maybe the catalyst. A suitable silica is used for the applications. So if you look at what kind of advantages actually it gives to the catalyst, is basically it improves the mechanical strength. In a technical terms, actually this strength is measured in the attrition index. Typically, most of these additives, they have attrition index less than 6, and silica plays a very important role in achieving the desired attrition into the catalyst. Of course, I mean to say this has also implications with respect to increasing the stability and life of the catalyst. Also, I mean to say silica salt. If you see at the surface, you have a lot of hydroxyl groups, and they have very good binding efficiency with the other matrix of the catalyst, especially the clay, the zeolite, or an alumina. So silica plays a very important role in binding the complete matrix and giving the desired properties the catalyst particle. So in addition, silica also imparts the mesoporosity. Basically, that is helpful in efficient mass transport, because there are wide range of hydrocarbons which are actually part of the FCC. Now, coming to the next slide. Just 1 minute. The presentation is stuck. Just 1 minute. Yeah. So now coming to the other part is basically a silica basically going into as a silica gel, or maybe into making of this molecular fuse based material. Is the slide visible?
Yes.
Yeah. Okay. Now the contribution of silica here is like there are different type of adsorbents which are used in the market, and most common adsorbents, either they are based on this zeolite molecular fuse, and the other class we talk about the silica gel. So zeolites, basically, as we know, I mean, these are basically aluminosilicates, and basically in silica gel nothing other than silica. And in molecular fuse, the most important thing is the molecular fuse are available in a different pore size or pore opening. So if you consider the different grades available in the market, if you see like zeolite A, which has a 3 Armstrong pore opening, there's a 4A, 5A. Again, I mean to say this pore opening is because of the exchangeable cations such as soda, potash, or calcium. And of course, there is also 13x, which is available in 8 angstrom size. Whereas if you compare that with silica, the pore size is very much wide, and some are available in the narrow range and some are available in also a wide range. And just if you see a plot besides the table, this is basically a plot which is plotted against the water absorption capacity versus the percent relative humidity. If you look at this plot, it's very clear. Like at a very low relative humidity, molecular Suez-based adsorbents are better compared to silica gel. Now, if you see at a silica gel, maybe at a relative humidity of 40, I mean to say silica gel is a better option if you consider any the humidity above this 40 relative humidity. So depending on the kind of requirements, there is a possibility to use different type of adsorbents and for different applications. So we have different grades which are available, which goes into this kind of packaging applications. As I said, this packaging, it can be some food grade materials also, or maybe electronic items, or any items which are very much sensitive to the moisture, wherein we can use these adsorbents. And here also basically silica is used in making of these zeolite molecular sieves, or in general I mean to say the silica gel. Now coming to the next this thing is basically silica in zeolites. So as I said, I mean to say zeolites, they are three-dimensional networks made of aluminosilicates. The speciality is they are having uniform channels and pores available, different pore size.
Excuse me, sir.
Hello.
Sorry to interrupt. Yeah, sorry to interrupt. 3 more minutes just for your information.
Yeah. So these zeolites find applications in many areas that will come to the next. But what is most important to know is how silica actually is used into zeolites. So basically, if you look at the procedure, synthesis procedure of a zeolite, basically there's an alumina source, there is a silica source, there is an alkali source, there is a template. Template is nothing but a structure directing agent, normally we say, and it also has some kind of a molar ratios for water. I mean to say this combination actually we call it as a molar gel recite. This is basically subjected to hydrothermal synthesis at particular temperature, anywhere beyond 150 degrees, depending what kind of the zeolite we are making, and at a particular temperature and time, and subsequently after cooling down we do a filtration, washing, drying, and calcination. And this zeolite in the as synthesized form, basically it has the alkali associated with that. So if you want to convert it into the acidic form, then ion exchange with either the ammonium sulfate salts, or maybe the nitric acid can be used for ion exchange. And subsequently, I mean to say, depending on the application, whether it is CST or on a fixed bed application, those can be shaped into different spheres or microgranules or extruded, or if it is a CSTR application, then it can be used as such in the powder form also. So there are different features this zeolite offers. So I will not go into those details, because I just would like to give you some examples of where these zeolites find applications. If you see in air purification, then basically it is SCR of NOx or VOC removal. In specialty and fine chemical acylation, oxidation. One of the examples is basically here I mentioned about TS1. This is used for 4 to 5 commercial applications for oxidation. That is phenol to catechol. You have cyclohexanone to cyclohexanone oxime. I mean to say epoxidation of propylene to propylene oxide, allyl chloride to epichlorine. All these are basically commercial applications wherein major the contribution in this TS1, it comes from the silica, and a suitable silica is used so as to ensure there is no contribution of the aluminum or the soda is associated with that. And there's a lot of catalyst which goes into amination, hydration applications in refinery, as I talked about the FCC or FCC additives. dewaxing, isodewaxing, hydroisomerization, isomerization. In petrochemical, again, alkylation, selective alkylation. I'll just give one example of the selective alkylation in the later slide, so that will be very, very clear. And of course, into the aromatic treatment, wherein, some kind of olefins which are associated with the aromatics, they are basically selectively removed by, some of the zeolites. And of course, there's a molecular use which goes into packing applications, drying of different gases, solvents, or even in the oxygen enrichment. So there's one more example, about silica, which goes into, the applications of pore regulation, or maybe we call it as a surface modification. So if you look at the application like the ethylation of ethyl benzene. So ethylation of ethyl benzene, basically using an ethyl alcohol. So there are three different products which are expected. Basically, one is orthoisomer, the other is, meta-isomer, and the third is, para-isomer. But normally, I mean to say, it is possible to, prepare or maybe, change the selectivity to the para-isomer, which is commercially more important, by, doing some surface modifications, of the catalyst. So this is one technology which is developed by IPCL. Now it is with Reliance. So this is basically a catalyst for PDEB. There is paradiethyl benzene application, where the selectivity of more than 97% for the para-isomer is, achieved. And this is done by, pore regulation of the zeolite catalyst. If you look at the right side, so there's the powder, actually, zeolite is, formed into an extrudate. And this extrudate basically is, pore regulated by using, some kind of a silica source. Of course, it's a highly engineered material, which type of silica to be used, and, how much to be used. That actually makes a big difference when it comes to application. So it is basically for pore regulation. This helps us, basically to fine tune the selectivity in a particular reaction. And this is one example of, silica basically used in one of the commercial applications. So in a nutshell, if you see the different type of silicas, what we discussed, I've just prepared a matrix which can give an overall view of where, the different type of silicas are used in either zeolites, catalyst support, adsorbent, binder, or, pore modifier. So this is basically the matrix which is based on, I mean to say, our own experience. We just, put it here. Now, coming to the last part of the presentation, what's most important, as Dr. Kannan said, like a lot of silicas has been, imported in India. So if you see, most of them which are imported are, this pyrogenic silica, silica salts, or alkoxy silicates. There's a lot of potential in India, for these applications, and also considering, their applications and the projections, what we see from the markets, there is a lot of potential to make this in India. And why, these all silicas, they are important to the absorbents and catalyst industry like us is, silica is available, in different properties. If you take any silica, whether it is precipitated silica, pyrogenic silica, there's no one grade. There are multiple grades, and every grade has some advantage, some disadvantage, wherein we can selectively, use some for the particular application, fine tune that application to make it suitable for that particular application. So this makes, a very important raw material, and the availability of this silica in, different properties, that's very much attractive for industry to try in, different applications. So, of course, as I said, this fine tuning of this silica can be a solution to many, problems for many of the industrial applications. And in the near future, basically, there's a lot of, niche applications may come from all these silicas, and this actually will open up, some new applications also, and maybe some new grades with, different properties. So this development will drive actually, and this way actually silica will going to play an important role for industry. So with this, actually, I thank you all for your kind attention. Thank you.
Yeah. Thank you, Dr. Sabde, for your detailed discussion about the different forms of silica and silicates. We also discussed about the synthetic procedures and how it influences the properties of silica for its diverse applications. If we have any questions, we can have one question quickly. There is any. Okay. Thank you, Dr. Sabde, for your presentation.
Yeah, thank you very much. Sir.
For your valuable time sparing us and explaining the details of the process, what is happening in Sudhkemi also. Thank you. Now, we are coming to the concluding point. Now, I request our head of the department, Dr. P.S. Subramanian, to deliver the vote of thanks.
As such, a separate vote of thanks is not required. I think my controller, Saravanan, has already thanked in every, after every speech. But still, as a customary, I think I have to deliver this. So this program is already started 2 years back, and slowly it has gone to a different platform. Finally, now we are holding this industry meet. After the industry meet, it is not sufficient. Actually, we need to have at least one full day for this. In the process of this, we have also visited some of the industries. One among those is Mother Silica. So it has given a different platform to learn as well as bring many things. Not only the silicon mission, it has given projects. It has given in the form of translational project as well as basic research projects that is being compiled in a different format. So at this occasion, it's really great day to have this 2-hour discussion. On this, my special regards and thanks to Dr. Sriram, who is our chemical team coordinator. Unfortunately, because of his plan, he is not able to join with us. But somehow our director, Dr. Kannan Srinivasan, who was molding from day one to this stage, whatever the success or whatever the achievements we have made so far, it's purely because of him, because he was the nut and bolt of this whole program. So the team Silicon is thanking as well as acknowledging his every effort. As well as today, he has spared the sufficient time to us, sparing his valuable time to discuss about the various forms of these proposals today. And I would also sincerely acknowledge the speakers, Dr. Swapan Ghosh from Pidilite Industries Limited, as well as Dr. Dhananjay Sabde, to deliver the great industrial experience with us and sparing their valuable time from their industries, as well as our sincere thanks to Dr. Bijan Kumar Roy from Mother Silica for sparing his valuable time spending with us this evening. It was really wonderful speech. Hope that the audience, students across the country, across the CSIR lab, as well as within the institute, as well as outside the institute, might have got benefited broadly by this interactive program. Your questions will be answered. Even if you did not put your questions, you can write it down. It will be answered. Beyond this, the team members, Silicon team members, my sincere thanks to Dr. Saravanan, Dr. Ankush, Dr. Govind for their wonderful contribution, for writing various, making every step success. As well as I would like to express my sincere thanks to the IT team, Dr. Devendra Singh and his team constituting Mr. Ritwik. Last 2 days he was really comprising and giving us training. Even yesterday we had the whole program has gone without any disturbance because of their involvement. I thank you all. Thank you very much for everyone who directly or indirectly contributed for this program. Thank you very much.
Thank you, sir.
Thank you.
We have one. Yes, we have one small. So if that is over, I think still there, line.
So, Mr. Ritmi, shall we close it now, the live session?
Yes, sir, I'm just closing it now. Thank you so much.
Thank you everyone for joining us today.